We are here to help.
Please note, always refer to your own course to ensure you are learning the method your instructor has used. This example will show you one of these methods. Consider the following scenario. You are interested in developing a drug for patients who have heart disease. In order to do that, you need to know the average heart rate of everyone in the world with heart disease. We'll call this the population. This population has a mean heart rate denoted by the letter mu, as well as a standard deviation for the heart rate denoted by the letter sigma. In order for you to get a value for the population mean, you would need the heart rate for every single person in the world with heart disease. But this would be impractical. A more feasible way to do this is to collect a sample of patients with heart disease, collect their heart rates, and calculate their mean and standard deviation, denoted by X bar and S, respectively. A different sample of patients would yield a different mean and standard deviation. In a hypothesis test, we are trying to use our sample information to make an inference about our population. Commonly, we want to see if we can use our sample mean to infer something about the population mean. Let's consider the following example. The dean of your school reported that the math course you're in generally achieves a final average mark of 60%. Your class this term had a total of 45 students who have achieved 66%, with a standard deviation of 7.1%. Marks in this class are normally distributed. With a confidence level of 95%, can you conclude if the dean should change the average in the report? Let's first make a list of the variables that we are given in the question. We know that the sample mean is 66. We also have a sample standard deviation of 7.1. There are 45 people in this sample. A confidence level of 95% means a significance level of 0.05. Finally, the question tells us that our data is normally distributed. We're now ready to start our hypothesis test. There are 4 steps to our process. 1. Determining our null and alternative hypotheses. 2. Calculating our observed test statistic. 3. Determining our critical value. And 4. Making our conclusion. Let's start with step 1. In this example, we are being asked if the dean's report is correct. The dean claims that the population mean is 60%. We can write this as mu equals 60. If the dean isn't correct, then the population mean would not be equal to 60%. Generally, the claim with the equal sign is set as the null, or H0. This means we should have the following. We are now ready to move to step 2. In this step, we need to first determine whether we are using a Z-test or a T-test before we calculate our observed test statistic. We can use the following flowchart to help us. Our first question is whether our data comes from a population that is normally distributed or not, to which we answer yes. Our second question is whether a value for the population standard deviation was given. In this case, we were only given a sample standard deviation, so we answer no. This means we will be using a t-test for this example. The formula for the observed t-test statistic is x bar subtract mu divided by s over the square root of n. Substituting the values we have for x bar, mu, s, and n, we get a t observed of 5.67. For step 3, we need to determine our critical value that is associated with a significance level of 0.05. We use the student's t distribution, or the t-table, to find this critical t value. We find the degrees of freedom for this question, which is determined using the formula n-1. Since n is equal to 45, we have 44 degrees of freedom. And we can simply go all the way down to the row labeled large. In this question, we were asked if our population mean was equal to a certain number, as opposed to less than or greater than a certain number. So this is a two-tailed test. Since alpha is equal to 0.05 in this two-tailed test, we are looking at the 4th column from the right. The t critical value is where the highlighted row and column meet. In this case, t critical is 1.96. Now that we have both our t observed and our t critical, we are ready for step 4. In this step, we want to compare the positions of t observed and t critical. Since this is a two-tailed test, our t-critical exists on both the positive and the negative tails of our distribution. The regions that are more extreme than our t-criticals are our rejection regions. We want to determine whether our t observed sits in either of our rejection regions or not. Since we have a t observed of positive 5.67, this value sits within our rejection region on the right. If our t observed is within a rejection region, this means we reject our null hypothesis. Rejecting our null hypothesis means we have enough evidence to support our alternative hypothesis, which says that the population mean does not equal 60. Therefore, our conclusion is that we have enough evidence to show that the average is different than the dean's report of 60%, and that the dean should change the average in the report.